Hi guys, I'm making a short video on pipes and interprocess communication using pipes. So we will be going through a brief of what is IPC, interprocess communication, that most of the operating systems uses and how to achieve it using pipes. Now, what is interprocess communication? Interprocess communication is a mechanism wherein an application process that is running on a system can communicate with another application process that is running on the same system using system calls. So, what are system calls? System calls are nothing but the application programming interface or the APIs or the function calls that are being provided by the operating system to interact with the hardware. For example, we write data into the memory using the write system call and read the data from the memory using the read system call. So these are basically the system calls. Anything that interacts with the hardware, anything where we use hardware needs a system call. Another example of invoking a system call is a network communication wherein we open the sockets, write into the sockets and then read from it. Now, each of the application processes are associated with a set of the memory locations wherein they can easily read and write. So, for an application process to communicate with another application process, which are associated with the two different set of memory locations, it is nearly impossible for them to communicate without a common communication channel. So, this is being achieved by the kernel by creating a common communication channel between the two application processes. So this is done by a piece of shared memory that two different applications can access, but at a kernel context as compared to the application context in which the application runs. Now, there are multiple mechanisms for the kernel to implement this common communication channel, which helps achieve the interprocess communication. So, pipes is one such mechanism which achieves the interprocess communication. So, with this short background of interprocess communication, let us look into the details of how IPC can be achieved using pipes. The concept of the pipe is similar to that of the normal physical pipe, where the water flows in from one end to the other end and flows out of the other end. So, similarly, the Linux also implements the pipe in a similar manner, where the data flows in from one end and out of the other end of the pipe. So, pipe has two ends. The end where the data flows in is called as the right end of the pipe, and the end where the flows out is called as the read end of the pipe. So as the physical pipe can carry the water in a single direction rather than bidirectionally, similarly the Linux pipe can carry the data in a single direction. So a single pipe is unidirectional, with two ends, one for the read end and the other for the right end. We do describe the two ends of the pipe with the name pipe descriptor. So we call it as the pipe DES. So there are two things in the pipe descriptor. One is the read end, which is pipe descriptor of 0, and the other is the pipe descriptor of 1, which is the right end. These pipe descriptors are being created by the pipe system call. So these are basically a normal integers. These are two normal integers which act as the pipe descriptor similar to that of the file descriptors. The pipes are being created by the pipe system call, which takes an array of two integers, which creates a pipe with two ends, which we call it as pipe descriptor of 0 and pipe descriptor of 1. So in order to create a Linux pipe, we need to declare an array of two integers as shown in the pipe descriptor of 2, and then pass this pass this array into the pipe system call. So the pipe system call on successful creation of the pipe will return a 0, else it will return -1. Now, in order to achieve bidirectional data flow using pipes, we need to create another pipe so that the data flows in the other direction as well. So we are doing this by creating another set of the pipe descriptors. Here we are creating an array of two integers called as the other pipe descriptors, which are being initialized by the pipe system call. Now let us consider a small example of an unidirectional pipe wherein one process writes the output to the pipe and the other reads from the pipe. For example, list is such a process where it lists the contents of a folder, and grep searches for any text in a particular file or a directory. So if I want to find out that a particular type of file is present in a particular directory, then in just by using a pipe wherein ls lists the contents of the directory, and I am using grep in order to find for a particular file. For example, I want to find the doc file, then I will do a ls pipe grep star.doc. So this lists the word.doc that is present in this particular folder. Now the output of ls is being fed as the input to grep. Now let us take a look at the operations that are related to pipe. First, we have to create a pipe using the pipe system call, and then we have to open the pipe for reading and writing. But the pipe system call by default does the open operation as well. It opens the read end of the pipe for reading and write end of the pipe for writing. As soon as the pipe system call is completed, the pipe is created on success, and then it is open for reading and writing. Later, we have to perform the read and the write operations using the read and the write system calls. And finally, after all the operations of the pipe are completed, we have to close the pipe descriptors that are being opened by the pipe system call. In order to demonstrate the pipe operations, let us consider an example wherein we have two processes. One is the parent process that writes the data into the pipe, and there is another child process that reads the data from the pipe. The parent process writes from the right end of the pipe, writes into the right end of the pipe, that is the pipe descriptor of the 1, and the child process reads from the read end of the pipe, that is pipe descriptor of 0. Now let us see how the pipe operations are being done in the code in this particular example of the parent process writing the data onto the child process using the pipe. For our example, where we have a parent and a child process and use a pipe for communication between the parent and the child process, we create the child process using the fork system call. The fork system call does nothing but it actually duplicates the calling process. It creates a process just by duplicating the calling process, and it assigns a new memory space, a new process ID to the new process. So here is the code for the fork. So I am here the child variable holds the pid for the newly created process. So child equal to fork. The fork returns the pid of the child. So in case of the child processor, this pid will be 0, and in case of the parent process, this pid will be non-zero. So this pid helps to differentiate between the parent and the child process. Now let us take a look at each stage of the pipe operations. At the first stage, we create the pipe using the pipe system call, for which we need an array of two integers. These represent the two descriptors of the pipe, the read end and the write end. So initially we create an array of two integers and initialize it to -1. Then we create a pipe using the pipe system call, wherein we pass this array of two integers, and then if the pipe creation is successful, we capture the return value into the return variable, and then if it is unsuccessful, we print the error using the p error system call, which also takes the rnum into consideration and prints the status of the error. Now, as soon as the pipe is created using the pipe system call, the next operations that we perform is the read and write operations. Considering our example wherein the parent process writes the data into the pipe and the child process reads the data from the pipe. So, in case of parent process, we just write the data. That is where we close the read end of the pipe. So, we pass the read end of the pipe, that is pipe descriptor of 0, to the closed system. Once the read end of the pipe is closed, we use the right end of the pipe for writing the data onto the right end of the pipe. The write system call writes the content of the buffer into the file descriptor. The number of bytes of data that is to be written is given by the count variable. So in case of success, the write system call returns the number of bytes that are written into the file descriptor, or else -1 in failure case. So we create a buffer which contains a string hello, this is a test string. So the contents of this buffer is being written into the right end of the pipe, that is pipe descriptor of 1. The number of bytes written is given by string length of the buffer. So on successful write operation, the number of bytes written is being returned into bytes written variable, so which we print here. Then in case of failure, it returns -1 and we print the error as well. Next we consider the read operation. So here in this example, the child process reads from the pipe and it does not write anything into the pipe, only the parent process writes into the pipe. So we close the right end of the pipe in case of child process. This is being done by the close of pipe descriptor of 1, which is the right end of the pipe for the child process. Now Linux system provides the read system call, which is similar to that of the write system call. So the read system call helps to read the data from the particular file descriptor into the buffer. The number of bytes to be read is specified by the count variable. On successful read, the read system call returns the number of bytes read and -1 in case of failures. So the code to read is as shown. We create a buffer of 256 bytes which is being initialized to \0. Now we read the contents from pipe descriptor of 0, that is the read end of the pipe, onto the buffer using the read system call. So at one given time we read 256 bytes or lesser. The number of bytes that are being read is returned into the variable bytes read, which we print here in the else part, and the data that is being read is also printed here. In case of errors, we print the error using p error. Once the read and the write operations are completed, we close the respective ends of the pipe. For example, in case of the parent process, since we were writing into the pipe, we were using the right end of the pipe. We had already closed the read end of the pipe. So after the write operations are completed, we also close the right end of the pipe using the close system call. Similarly, for the child process, we were using the read end of the pipe and we had already closed the right end of the pipe. So for the child process, once the read operations are done, we close the read end of the pipe. Let us now write the program for our example pipe program, wherein we are trying to communicate from the parent to the child process using pipe. So let's start with the IO stream, include IO stream. So this is for the input and output, hash include uni std.h. This is for the pipe related operations, and hash include string.h. This is for the any string related operations. Then we will include the namespace std, and now we have int main int c star v. So here we will just first create a PID for the child process, for the child process process. So this will be PID underscore t. We can either use PID underscore t, which is child, or else an int, and initialize it to -1. So finally we are creating pipe descriptor, a pipe descriptor which is for the read end and write end. This will be pipe descriptor of 2 for a single pipe. There will be 2 ends, so this is an array of 2 integers which are initialized to -1. Now we will have an int return val which will be equal to -1 to hold the return value of any of the functions. Now let us create the pipe. Let us create a pipe using the pipe system call. So let us use this return value to hold the return value. So pipe of pipe descriptors. So descriptors. Now we have to check if the pipe is creation is successful or not, or else we will have to print and we will change parent. Now once we print everything, we know that we are using the child process to read data from pipe. So we will first, since we are just reading the data, we will close the close the right end of the pipe of the pipe. So close of pipe descriptor of 1 is the right end. Now similarly, we use the parent process for writing into the pipe, write into the pipe. So we will close the read end of the pipe. So close of pipe descriptor of 0. So here we are closing the read end of the pipe. So now let us go ahead and finish the writing part. So in order to write the data, let us create data that will be present in buffer. Hey, this is test string. Hey, this is test string. So now we have to write. Let us write the data 5 times. So for collecting the number of bytes written, I am creating a variable called as bytes written equal to -1. Now for 8 I equal to 0, I less than 5, I plus plus. So I will be writing bytes written equal to write system call with right end of the pipe comma buffer comma str length of buffer. So whatever the data is there, that is the maximum length that is being written at once to the pipe descriptor of 1. Now we will print the bytes written. Since this is parent process, I will just write parent, then bytes written, bytes written, bytes written, and then let us print the data that is being written. Again, since this is parent, data written, this will be buff with an handle. Now since we are done writing the data, let us close the right end of the pipe close of pipe descriptor of 1. Now exit the process, exit the parent process, exit success. So similarly, let us write the code to read from pipe. So here we again create a buffer to hold the data, which will be of 256 bytes, and we will initialize all the bytes with null termination character. Once we initialize it, we will create bytes read variable, which will be initialized to -1. Now since we don't know how much data is being written onto the pipe, to read we will use a loop, and it reads until there is a end of file, which is nothing but 0. End of file being encountered, which will be nothing but 0 bytes on read. So bytes read equal to read system call with pipe descriptor of 0 comma with read into the buffer with a maximum of 256. Now let us print what is read. So again, this is child process. So bytes read, bytes read, and let us print what is the data read. Child data read buff read end of pipe use of pipe descriptor of 0. This is the read end. Now exit the process, exit the child process exit of exit success. So this is the entire program wherein the parent writes the data into the pipe and the child reads the data from the pipe. Now let us compile our program g++ pipes.cpp. Then we have /a.out. So here you can see the main, since fork duplicates the process, we are getting this print two times, one for the parent and one for the child. And this is the parent PID, that is 832, and the child PID 833. So the child variable is 833 inside the parent, whereas inside the child it is 0. So this is the if and the else block that we were speaking about. Now the parent, the data return is hey, this is the test string, and the child also reads the same data. So this continues, and finally the child reads the data, that is 0. This is where the child exits, and similarly the parent. So this is all about the program. Now let us introduce some breaks to see what happens with the pipes. So for example, in case of the, I'll just introduce character ch equal to \0. So I'll just introduce in both the cases, c of ch from the child as well as in the parent scene ch. This is to see what happens when what actually happens due to when the processes are running. So here if we recompile it and then run it. So here there are two processes that are being created. So let us have a look. ps-a, this is 839 and 840. If you see, 839 and 840 are the two processes that are being created. Now let us look whether the pipes are being created or not. So I am using ls of -p, which is the list of the which lists the file descriptors that are open with respect to a particular process. So if I do 839, which is for the parent process, you can see it has opened up two pipes. Pipes 973, which is for reading and writing, and 840, again this also has the same 973 for reading and writing. This is because I have put I haven't closed the read end or the write end of the pipe. I'll just show you show the changes. So for example, now if I kill this process, and now if I put another ch just after the closing, and now I'll recompile the program and run the program once again. So let us check the new processes that are created, 851 and 852. So ls of -p 851. So you can see the parent process has created again the FIFO 987, and for 987 for read and write. Similarly 852 is that of the child. Now if I go back and say x, so now if I check for the parent, it is still there. For the child, for the child process, it has closed one particular FD. So similarly, if I give one more x, so let us see. For the parent, it has closed another FD. Now another end of the pipe. Now we run the program. So this is all about pipes. The system actually creates the pipe for, or the FIFO, in order to communicate between two processes. You know, So this is all about pipes, which we call it as FIFOs or unnamed pipes or temporary pipes, or also denoted as a pipe symbol on the keyboard. So usual examples include the LS pipe and grep, which I have already shown. Then it is again smaller recap as it is being created by the pipe system call, and it creates a pipe with two descriptors, one for reading and the other for writing. And the pipe system call not only creates the pipe but it also opens the pipe, so there is no explicit need for the pipe the for the open system call. So this is all about pipes, guys. Thanks for watching.